Howdy, y'all. So, I'm so sorry I am not there today, but you can still have fun because it's Friday. Um, so, what I'm going to have you guys do today, first of all, obviously, you should say your daily mantra. Go ahead, I'll wait. Go ahead and say it. I'll wait. Go, okay, I'll count you off. Here we go. Here we go. On the count of three, loud and proud. Or maybe, semi-quiet because I think other people around you are probably like, listening to the recording. Yeah, go ahead. Okay, so on the count of three, one, two, three. I am good at math. Huzzah! I talk faster than I write. So there it is. So what we're going to do, I am going to give you some quick guidance about Go on your homework from last night, which was, I believe, section 3.2. Yes, section 3.2, Go. Specifically the graphs at the end, because I want y'all to graph those. There are 9 graphs. And I think that maybe you may not have gotten to all of them for your homework. So I want you to work on some of those today. So I'm going to walk you through a couple of those so you know what to do. And then I'm going to give you some notes about polynomials and end behavior. And then I'm going to do a couple of samples for tonight's homework, which I would like for you to do in class because I'm not there. So you have time to do that in class, which is 3.3. Section 3.3, we're going to do the whole thing. So go ahead and go to section 3.2, Go. And let's start at number 18, or no, sorry, 17 and 18, 19. We're going to do those graphs. Okay, so here we have number 18. Number 17, you guys should be able to graph. That is a linear graph. You have your x-intercept is 2, and you have your slope is going to be just up 1 over 1. So just go ahead and draw your axes on. Y'all can do that. I have faith in you. 18. So now we're going to get a little bit more difficult. This is anybody know x squared means? You are correct. That is a quadratic. So what are we expecting it to look like? Starts with a P, ends with arabola. Good. It's a parabola. So that's what we know it's going to look like because it's a quadratic, and that's what quadratics look like. So what I would like for you to do and kind of get into the habit of doing, what we're developing here is kind of an idea about what parent functions look like. So all linear functions that just have x will all be a line, straight lines, right? Going up or going down. All quadratic functions are going to be parabolas, right? They're going to be kind of a U-shaped curve, so they'll look like that, or they might look like that. And then we're going to talk about exponentials, and then we have a square root and an absolute value as well. So I want you to get used to what these graphs look like. Do they look like a curve? Do they look like a line? Etc., etc., etc. So the first thing I'm going to do here is I'm going to make some axes because I don't have any axes on my graph. So let's go right, I don't know, like right about here. I'm just going to draw. Oh, well, just pretend that's on there. And then I'm going to go like that. Okay, pretend that's straight. Okay, now, since I don't know what this graph is going to do, whenever you're in doubt with a graph, y'all just make a table of your x and y values. And then you can use the points that we always use, which are -2, -1, 0, 1, and 2. And just plug those in, plug it in for your x right over here. Let me do it again. Bloop, right there. Except pretend it's a plug. Make it a plug. It's a plug. Plugging it in. There you go. Plug it in, plug it in. And then we can figure out what our y values are going to be. So let's do it. I'm going to start with -2. So h of -2 equals -2 squared plus 2. Y'all, what's -2 squared? So -2 times -2. If you said 4, you are correct. And then 4 plus 2 is 6. So an x is -2, y is 6. So y'all, what that means on my graph, I can go over to -2 and then up to 6, which puts me right here. There's a point. Voila. Let's do the next one. H of -1. So same thing, plug it in, plug it in. -1 squared plus 2, -1 times -1 is right. +1 plus 2 is correct. 3. So I'm going to put a 3 right there. I'm going to go over to my graph, and I'm going to say graph, that's -1, and then up 3, so right about there-ish. Moving right along, I'm going to move to H. Oh, golly, that's not an H. Let's write that again. H of 0. So that means 0 squared plus 2. And guys, y'all, notice that whenever I'm plugging something in, I'm putting it in these handy-dandy parentheses. I do want y'all to get into the habit of every time you're plugging something in, go ahead and plug it into these parentheses. Put the parentheses in so I know exactly what you're doing. Okay, so 0 squared is 0 plus 2 is 2. I don't even have to have a little extra step for that. So 0 comma 2 is going to put me right here. Bing. Then I have h of 1. So I have 1 squared, nice parentheses, plus 2. 1 squared plus 2 is just 1 plus 2, which is in fact 3. So it looks like I'm going back up. So 1 comma 3 is going to put me right there. And then finally, oh, I forgot to plug that into my table. Finally, I have h of 2. So 2 squared plus 2. 2 squared is 4 plus 2 is 6. Or, how do they say 1, 2, 3, 4, 5, 6, 6 in German. So 6, 2 comma 6. So I'm going to go to over 2 up 6 right there. Look, just like we had said it would be, we have a parabola. And I could have probably guessed that it was going to be bumped up 2 units because this guy right here means that it's going to be bumped up 2 units. So, voila, I have graphed it. I've made a table. I'm very excited about life. I'm going to go to number 19. Welcome to number 19. So we're going to do the exact same thing here. We're going to graph it. This is an exponential graph, and I know that because the x is upstairs in the exponent. We can also talk about this as a geometric series because I am multiplying every single time. So I know that the shape of this graph is going to be something like that, kind of a swoop type thing, like so. So let's do the same thing. So I'm going to have a table over here. I'm going to have my x and my y. There's my fancy table. And let's just plug it in. I'm going to start with my usual points, -2, -1, 0, 1, and 2. Y'all, if you have other points that you really like to use, I guess use those points, but these, for my money, are the easiest one to use, and they get you exactly what's going on around the origin. Let me go ahead and put in my axes here. I don't know why they didn't draw axes on these things. It's a little strange if you ask me, but that's cool. You know, they can do what they want to do. Okay, so let's start doing some math. So I'm going to start with, let's say, f of -2, which means 2 to the -2. Oh, golly, let me write that -2 again. That was a little rough. -2, there we go, plus 2. So what is 2 to the -2? Remember, that is the same thing, this guy is the same thing as 1 over 2 to the +2, which is in fact 1/4. So I've got 1/4 plus 2, which is the same thing as 2.25. I am going to leave it in decimals here because I know y'all like decimals more than fractions, even though I think you should be comfortable with both. But that's a story for another time. Okay, so negative 2, 2.25, so that means over here on the graph I should have a point at negative 2, 2.25. I'm going to have to kind of estimate a little bit where 2.25 is. I'm going to say it's there-ish. So there's my point on my graph. Let me get back over here and do f of negative 1. So that's going to be 2 to the negative 1 plus 2. And 2 to the negative 1 is going to be 1 over 2 plus 2, which is 2.5. So then I'm going to go to my graph, and I'm going to go over to negative 1 and up 2.5. Again, a little estimation there-ish. All right. Then let's move on. Keep plugging in, plugging in. F of 0 is, oops, I wrote 0 and that's not right. 2 raised to the 0 power plus 2. What is 2 to the 0 power? Turn and tell your neighbor right. Actually, don't, because they might be at a different spot. Tell yourself, whisper to yourself, whisper, what is 2 to the 0 power? If you said 1, you're right. So 1 plus 2 is 3. So, oh my gosh, y'all, I haven't been putting these up in my table. So 0 comma 3, let me just put that on my graph real quick. That's an easy point. I don't know why I made that bigger than all the other ones, but that's fine. Next we have f of 1, so 2 to the 1 power plus 2. 2 to the 1 is 2, plus 2 is 4. So when x is 1, when I plug in x, I get 4 as my output. Let me graph that one real quick. 1 comma 4, so I'm right there. And then last but certainly not least, in fact, it's actually the greatest, is f of 2. So 2 raised to the 2 power plus 2. 2 squared, y'all, is 4 plus 2. So when I plug in 2, I get 6 as my output. So I'm going to go over 2 and then up 6, which puts me right there. And we have a lovely swoopy graph. So let's see if I can draw it in without goofing up here. Here we go. Yeah. Awesome. So that is my exponential graph. And you'll notice again, it's pretty much the same thing as a regular exponential graph, except I scooted it up 2 units, which makes sense because it says plus 2 right there. So I scooted it up 2. Huzzah! Dunzo. Okay, what I would like for you to do is pause this, go do all of those graphs. I want you to go all the way up to 25. Make a table if you don't know what the graph is supposed to look like. Pay attention to what's going on with things like this, with the plus 2's on the end, or if the plus 2 or the minus 2 is inside the parentheses, how does that affect your line? Think about all that stuff. If you get stuck, what you can do is you can go to Desmos.com, plug in that function, and it'll help you out. Please only do this as a last resort. I would really, really like for you to make a table first, to know how to graph this by hand first, because on a test, you will not be allowed to use Desmos.com. You will be allowed to use your brain and a scientific calculator. So I want to make sure that you know how to do this on your own. Okay, so pause this. When you're done, come back with a blank sheet of paper, and I'm going to give you some notes on polynomials. Okay, go forth and graph. And, by the way, when you're done graphing, compare to your neighbors, see if you have the same graph, see what's going on. And then I also gave the substitute a key so you can check and see if your graphs are right up there with him. Okay, have fun. Graph, go. Okay, hopefully you are done graphing, and I am here now to give you some notes, so you will need a blank sheet of paper to write down some stuff about polynomials. And most of the stuff, y'all, is just going to be some vocabulary and some descriptions about what polynomials are and what they do on a graph and all that good stuff. So, can you tell me what is a polynomial? First of all, what does poly mean? This first part of the word right here, poly. Anybody know what that means? You're right, it means many, like polygon or polyjuice potion or anything that has poly in front of it. So polynomials means many nomials, which kind of means, well, it can mean name. I've also heard it talked about as meaning numbered, but basically it is an expression with more than one term. So an expression with more than one term. So for example, let's do y equals x cubed plus 3x squared minus 5x plus 1. Look at that beautiful polynomial right there. So I've got, well, let's count. 1, 2, 3, 4 different terms. So this is, in fact, a polynomial. Something else I would like to point out just kind of while you're looking at this is notice how the exponents are in descending numerical order, because I have 3, 2. If there was an exponent here, that would be 1. If there's an exponent here, it would be 0. So whenever you're writing polynomials, you want to write them with the largest exponent first, and then kind of work in descending order. So the second largest next, then the next, and then the next. Okay, when I talk to you about the word degree, the degree of a polynomial is equal to the largest exponent on a variable. The largest exponent on a variable. So, for example, with that example that I just wrote up there, the largest exponent on a variable is that 3 right there. So this guy is a third degree polynomial. You could also say it has a degree of 3. So I'm going to write down some polynomials here, and I would like for you to tell me what their degree is. So let's go x to the 17th plus x to the 12th minus 5. I'm going to pause this, write it, so you don't have to listen to me talk about it. And here we are. Here are our examples. So let's work through these, and I want you to tell me what the degree is of each one. So let's start with this guy right here. That's supposed to be a star. Let's go. Okay, so what is the degree of this? The degree is equal to the largest exponent on a variable. So, Shazam, this is a 17th degree polynomial. What about this guy right here? The largest exponent on a variable is right there, so this is a 5th degree polynomial. Let's go down here to this puppy. The largest exponent is right there, and that is a 7th degree polynomial. And then finally, let's go to this guy. Oh, this is a little tricky. I did this on purpose because the largest degree technically on all the variables is 1. But you are thinking about this in standard form. So if you multiplied all of these guys out, you would have your very, very first degree, if you FOILed all of these out, would be x times x times x. So how many x's would you have multiplied together? That would have been 3 x's. So this is a 3rd degree, because in standard form, you would have had x to the 3rd, so 3rd degree, okay? Okay, write this down. Pause it if you haven't gotten all this, because I'm moving on. Okay, the next thing that I want to talk about polynomials is their graphs. So you know how to find the degree. Let's talk about graphs. Graphs. So let's say you have a graph. There's one. That's great. And then let's say you had a polynomial on that graph. Delightful. That's just beautiful. So what I want to talk about is a couple of things. So first of all, every single polynomial graph has a smooth, curved graph. It's not going to have any sharp corners. It's not going to have any breaks or holes. It's not going to have, I know it will have holes. I take that back, but it's not going to like stop at one point and then start up like, 3 units over. It's got to be a continuous graph, smooth curves, all that good stuff. So here we have, this is a lovely polynomial graph right here. So we were talking about degrees, and I want to talk about 2 things here. First of all, I want to talk about the word roots. So a root, and you talked about this last year with quadratics. When you're finding a root, what you're finding basically is the x-intercepts. X-intercepts. So on this particular graph right here, I have 1, 2, 3, 4 roots. And your roots are usually going to be equal to the degree. So if I have 1, 2, 3, 4 roots, that usually means it's a 4th degree function. So the biggest exponent is going to be x to the 4th. So roots are basically where I cross the x-axis. Another word for roots that you might see thrown around every once in a while is the word zeros. So these are my zeros, which makes sense because it's where y equals 0. All the places where y equals 0. Okay, the other thing I wanted to talk about is something that we call end behavior. End behavior. And end behavior, y'all, is this fancy schmancy way of talking about what the graph is doing as you go to the ends of the graph. So the ends of the graph are going to be all the way this way, and then all the way that way. And you might think to yourself, well, self, what happens when I'm all the way to the left? What even is over all the way to the left? Does anybody know what's over all the way to the left? You guessed it, it's negative infinity. If I keep going and going and going and going and going all the way to the left, I will get to negative infinity. Technically, you won't ever get there, but it's a theoretical construct, whatever, you got it. And all the way to the right, if I just keep going forever, is positive infinity. Hooray! Okay, so for this particular graph, as I'm headed out all the way to the left, so as x is approaching negative infinity, because this is my x-axis, right? The horizontal axis is my x-axis. So as I'm approaching negative infinity out to the left here, what the heck is my y value doing? What is f of x doing? Because remember, when I say f of x, that's the same thing as saying y. So what is the y value doing? Is it increasing or decreasing? Does anybody have a guess? I can't hear you, but I'm going to pretend I heard somebody say increasing, and you are correct. It is going in an upward direction. And so since it's going in an upward direction, what's going to be up all the way up that way on the y-axis? You are correct, infinity. That's what's all the way up that way on the y-axis. So what I can say when I'm describing end behavior is I can say, well, as x approaches negative infinity, so as I'm going all the way to the left, then f of x approaches positive infinity. So x is going all the way to negative infinity, and while I'm doing that, the graph, the green line, is going up and up and up and up and up to positive infinity. Then I want to know what's happening with the graph as I'm going to the right, all the way to the right, forever. As x goes to the right, there's my infinity, where is the y going? Where's the y value going? The y value, my friends, is going up and up and up and up and up again. And we've already said what's up there? Infinity and beyond. So what I can say is as x approaches positive infinity, bloop, f of x approaches also positive infinity. So x is going up, y is going up, everybody's going up. We're having a grand old time. So that is end behavior. I'm going to give you one more example of this on the next slide. So write this down, pause it, write it down if you need to, and then I'm moving on. Okay, so here's our next graph. It's delightful. I'm having a good time. First of all, where are the roots? If you would like, point to your screen and identify the roots. If you pointed here, poof, here, poof, and here, poof, those are my weak attempt at explosion noises. You are correct, and you have identified the 3 roots of this polynomial, which probably means this is a 3rd degree polynomial. Since there are 3 roots, there are probably it's probably a 3rd degree polynomial. Okay, let's talk about end behavior. End behavior. So we're going to start with this one. As x approaches negative infinity, so that means as I'm going this way and this way and this way and this way forever toward negative infinity, what the heck is my y value doing? And it turns out my y value, my f of x, is going up and up and up and up and up and up and up, just like the last example, which is toward infinity. So I'm going to say as x approaches negative infinity, f of x approaches positive infinity. Then let's look over to the other side. As x is going this way and this way and this way and this way for life up toward positive infinity, so as x approaches positive infinity, what is my y value doing? What's the function doing? Y'all, look, it's headed downward, and what's downward on the y-axis? If you said negative infinity, you are correct. It is in fact negative infinity, so I'm going to say f of x is approaching negative infinity. So guys, that's the end behavior. That's all you need to know about end behavior, and that, believe it or not, is the end of our notes for today. I know. Well, no, it's not. Okay, I lied. I'm sorry. Don't get excited. Don't put away. Get it back out. But I only have one more small thing to show you. Okay. Pause this. Write this down because I'm going to a blank one next. Okay. What I need to talk about very, very quickly is degree and end behavior. But this is very, very handy and it'll help you a lot. So, what you know, and if you don't believe me on this, you can go to Desmos, you can pull out a graphing calculator, and you can find out all this information for your own self. But if you know the degree of a function and you know if the leading coefficient is positive or negative, you can figure out exactly what the end behavior looks like. So, I just said a fancy word, and I should define that word before I move on. The word I used was leading coefficient. Does anybody know what leading coefficient means? Anybody? Anybody? Great, good. Leading coefficient is, in fact, the number in front of the first variable. So, for example, if f of x was equal to negative 2x squared plus 3x minus 5, Which one of those is a leading coefficient? If you said -2, then you're right. You're totally right. That is a leading coefficient. It's the number in front of the first variable. So leading coefficient. So let's make a quick table real quick. Let's make the table, I guess we'll make the table black. That's fine. So this table is going to be 4 squares, like so. 4 squares. And here are going to be the entries for the table. We're going to say even degree up top here, odd degree up top here, and then over here I'm going to say positive leading coefficient, and then this one is going to be a negative leading coefficient. Okay, so if you need to pause and write that down, get all that down, go ahead and do that. I'll wait while you put it on pause. I'll wait. Go ahead. Okay, I'm moving on. So here we go. If you have a function that has an even degree, so for example, y equals 3x to the 4th. Even degree and a positive leading coefficient. And remember, y'all, the leading coefficient is this number right here. So that number is in fact positive. Another example of this could be y equals 1/2 x to the 6th. So degree is even. That is even. 4 here, 6 here. And the leading coefficient, 3 there, 1/2 here. Those are both positive. When you have this situation, your end behavior is going to look like a touchdown. So you're going to have both sides going up on your graph. So I drew that in arrows. I should write it out. So here we go. As x, that's an S. Let's back up, back up, back up. As x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x also approaches positive infinity. So f of x is going up to positive infinity all the time, every time, for an even degree with a positive leading coefficient. Now, what about an even degree with a negative leading coefficient? What do you think happens? Are there any guesses? And an example of this would be just like -3x to the 4th. When this happens, it just flips. So it just turns down, like so. So as x goes to the left so far, then f of x also goes down, 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 down. And then as x goes to positive infinity, so to the right, to the right, to the right, f of x still is going down to the down to the down. Okay, this is a terrible looking chart. I'm so sorry for my handwriting. It is dismal. Okay, so odd degree. So let's look at some odd degree. So we have y equals 3x to the 5th, or y equals 1/4, I don't know, x to the 9th, I don't know. Whenever you have that, you're going to have a function that's going to go, it's going to look like that. So let's write that out. So as x goes to the left to negative infinity, what is the function doing as x is going to the left, to the left, to the left? The function is going down to negative infinity. And as it goes to the right, as x goes to positive infinity, the function is also heading up to positive infinity, like so. And then finally, when you have a negative leading coefficient, so for example, just like negative 3x to the 5th, or negative 1/4 x to the 9th, it's just the flip of that. So it's going to go. Okay, so let's record that. So that means as x goes to the left, over to negative infinity, f of x is going up. So that's up to positive infinity. And then as x is going toward positive infinity to the right, f of x is going down, so down to negative infinity. Guys, I went outside of the box, which makes me sad. It's okay. We can do it. It's all right. So this is kind of your cheat sheet. If you know the degree of a polynomial, if you look at a polynomial and you can see, oh, it's got an even degree and it's got a giant negative coefficient out front, I have an idea of what it's going to do just by looking at the polynomial. I have an idea about what its graph is going to do, which is very, very, very exciting. So what I would like for you to do, I would like for you to pause this right now, and I want you to go to your books and do, or your packets, whatever, and do section 3.3, the main activity. So it starts with, what does it start with? It starts with like, oh, all about behavior. And it's like, determine the function type. So tell me, is it a quadratic? Is it an exponential? Is it linear? Is it cubic? What type is the function? And then talk to me about the degree and talk to me about what the end behavior is. And I want you to use this type of notation, that as x approaches infinity, f of x approaches something. So use that notation. And then you're going to do that with some graphs, and then you're going to compare and contrast some stuff. So I want you to pause this, do that, and then your homework, which you should complete in class, because I know this has been a long video, but you should be able to have time to complete at least some of this in class. Ready, set, and go are your homework. So the next slide right after this is going to be number 7, I think, on ready, the very first graph that they want you to do, just in case you're having some difficulty. But most of that should be pretty straightforward. I believe in you. You can totally do it. So have fun. And then the next part, like I said, will be ready. Rock and roll McDonald's. If you need help, I'm going to go over this problem. This is number 7 in 3.3 ready. This should be fairly easy, but I just wanted to cover this just in case. So you have this function up here, this equation right here, that they would like for you to graph and talk about the end behavior. So what do you know about this equation? Here's what I know about this equation. I know that it is a quadratic because it's got two x's that are being multiplied by each other. I know that it has roots or x-intercepts at x equals 3 and x equals -4. And I know that its shape, since it's quadratic and it doesn't have a negative in front, its shape is going to be like that. So I can go ahead and fill out this answer down here. As x goes to the left, f of x, the y value is going to go up to infinity. As x goes to the right, to positive infinity, f of x is still going up. It goes up on both sides. And now it's asking me to graph it, which should be pretty straightforward. If you wanted to FOIL that out, you totally could, just to kind of see what the y-intercept is. If you do FOIL it out, you get, let me actually change the pen there, back up. Let me change the pen for a second. Okay, so if you do factor this out, or sorry, FOIL it out, you get x squared, because x times x is x squared. Then you get x times 4, which is 4x. Then you do the inside, so minus 3x. And then you do -3 times 4 is -12. And then obvi, I can combine these two things in the middle right here. So what I end up with is x squared plus 1x minus 12. So this guy right here, that's my y-intercept. So I can go ahead and graph a y-intercept at negative 12. So that means, I think I'm going to change my scale a little bit. So instead of having 1 as my y-scale, I think I'm going to say that's going to be negative 2, negative 4, negative 6, negative 8. Anytime you change a scale on a graph, y'all, please make sure you label it. Don't think that I can figure out what you're doing. Assume that I know nothing, Jon Snow. Okay, let's get to graphing. So, I have a y-intercept at negative 12. I know I have x-intercepts at positive 3, so right here, I'm not going to change the scale on my x-axis. I'm going to leave that the same. And you might be asking yourself, Self, can I just change the scale on one axis? And the answer is yes. You bet your boot you can. No problem. So I changed the scale on the y-axis, but not the x. That's fine. So then my other x-intercept is negative 4, so that's right there. And then, y'all, I'm just going to go ahead and sketch a graph of that. Wow. Well, I'm just going to ask you, because it's late and I would like to go to sleep, pretend that that's actually touching the point right there. But that's what your graph should look like. Boom. Okay, so one more time, just to make sure you have all the directions straight, you need to do all of 3.2, 3.3, including the main task and ready, set, and go. Please show your work. Please make sure I know what you're talking about. Talk to your neighbors. Remember, we learn better together. And that should be good. All right, I will see you guys on Tuesday. Have a fantastic weekend. And I'll talk to you soon. Okay,